All right, recording is rolling. It is Wednesday, May 1st, 16 days until the exam. All right, so we got a weird schedule today. We're on this type schedule. Here in the left column, we put today's schedule. So we started in homeroom period, right, for 2.5 hours. Right, that was extended. There's some technical difficulties going on with exams. Yeah, thanks. Okay. And then all right, so we're doing the schedule. There's no 6th period today, and there's no 7th period today. Right? So 5th period is going to be your last period. Right? Now, my other AP class is 6th period, so I'm not going to see them at all. So do some last minute modifications here. Right? Tomorrow, you're going to hit all your classes. There's just these weird times. So first period is going to be 2.5 hours, and then you go from there. Okay, so you guys get that? Right. Anybody watching at home who's curious, I do have C lunch. So this is going to be a rotating schedule. So all your classes, it's going to rotate through. I did post to Google Classroom. Let me show you guys exactly what I'm talking about. I posted to Google Classroom this morning the schedules for the next couple of weeks. So I'll find this here. There's you guys. All right. So here, I just uploaded this morning. May schedules. I'll show you guys this file. All right. So here's today. Here's tomorrow. Right. And then do you guys see tomorrow? You're going to start first, go through 7th. It's just, yeah, like weird times. Right. So you have lunch with your, what class tomorrow is lunch tomorrow? 3rd period. Right. So no, what lunch at, right? And then here's, right. Now this is 5, 6. That's Monday. Right. So Friday is just Friday schedule. And then on Monday, guys, what's your very first class on Monday? 2nd period. And you guys see it just rotates through and so on. And then Tuesday starts with 3rd period. Okay. So you guys see that? Right. These are all there, so you guys can access that file and know what costs what. Yep.
Can you do this class on Monday because of my DPW?
Oh, okay. All right. Yeah. Thanks. Yeah. So yeah, we are in like testing season, so a bunch of guys have different tests, different times, different days, right? So in my attendance, it'll show up. It'll just say that you guys are testing. So yeah. Right. All right. So got that going on. All right. So let's look at right. Flip back over here. So what we're going to do is put off the FRQ scoring until probably tomorrow. I think tomorrow would be a good scoring day, right? And for today, yeah, I'll take any questions that you guys ask, and then I'll pull up some multiple choice questions to finish off the class, right? And the first question got queued up is, what are the forces, say, like going around a Ferris wheel, right? So a Ferris wheel would be like a vertical motion wheel. Right? Actually, let's do this. Let's look at a complete picture, because yeah, there was a free response question you guys had that we're gonna again like score tomorrow as my plan. Right? It involved a Ferris wheel, but they only asked for the forces at one particular point. I think it was right. Let's do this. Let's do a Ferris wheel at constant angular velocity. Well, here, angular velocity. That's what omega is, right? You guys know that, right? Versus, I'm gonna look at a slightly different scenario. Let's look at a ball on a string in a vertical circle, right? And the Ferris wheel is also a vertical circle too, right? But the physics are a little bit different. And let's have this as, I'm gonna say at constant mechanical energy, right? So these are 2 different scenarios that are gonna play out a little bit different, okay? Right. Again, the question you guys got was just at one particular point was the forces look like, right? But I'm gonna look at several points for these 2 different scenarios. Okay, you guys got that? Okay, you guys got your notes out? You guys got paper for notes? Good. Get you guys paper for notes. Paper for notes.
Is that what we're using this paper for?
Okay, the work that you gave you, I was gonna do when we get to multiple choice questions, have you guys write down a multiple choice answer, and then see if you got it. Yeah. Right out past on me. All right, paper for notes. Okay. First of all, it's gonna be guys draw a couple of circles to set up the scenarios. All right, so we know there's some kind of circle going on for each one of these. Okay, got a circular Ferris wheel, got a circular motion of, say, like a ball and a string, something like that. Right. And I want to look at 4 points. Let's look at the very top and the very bottom. So like if you're like in a carriage moving around for the Ferris wheel, it's something like this, a carriage, right? And then also the sides. So what is it like right at the sides? What's going on? Right? Something like this, right? And here's like a, say, a ball on a string going around, okay. Or it's tied to the string in the middle. It's going around. Okay, something like that. Okay, so you guys got that? You guys know it's like a ball on a string going around. Something, some tangential velocity. Okay. Okay, so you guys good? All right. So let's do 8 free body diagrams. Right, we'll do 4 for the left and 4 for the right. This free body diagrams. Okay. Remember, these are rotating. So the Ferris wheel is rotating some constant angular velocity. Right, and the ball on a string, well, if it's vertical for constant mechanical energy, guys, constant mechanical energy, the ball on the string, is it like speeding up and slowing down? Yeah, I think it's speeding up on the way down and it's slowing down on the way up, right? So it'd be like a changing velocity, right? You're changing speed, I should say. Okay. Now, I have seen APS set up the premise where maybe it's like constant speed going around, but that would be a weird case, right? They'd have to tell you that for you to assume that would be the case. Okay. All right. So, all right, let's pick one of these. I think the question that you guys were asked was, what's the forces down at the bottom? Is that what you guys were asked? Right. So let's start with that one. Right. I'll put a center mouse dot right there. Right. Let's say like you're sitting down on the bench. Let's say you're sitting on top of a scale, right? Like a bathroom scale. You're sitting on the scale on the bench, and that scale is actually reading what kind of force? A normal force, exactly. So if this was a free response question, and you guys had to draw and label forces, you guys know you're going to label your forces, right? Not just draw the force vectors, right? Right. Did you guys have that one finished? You guys have that one? All right. Let me take a quick glance around the room. Right. You guys are drawing a free body diagram. We're going to start with, if you're in the Ferris wheel at the bottom, right? What are the forces acting on you at that moment? The forces at that moment. Ooh. Oh, and guys, remember it's rotating, right? It's got some angular velocity. So are those forces going to be exactly the same magnitude? Right. And if you draw them with this correct magnitudes, then which force would be bigger? Yeah. So it looks like that, I think. All right. Yeah. All right. Yeah. Looks like some of you guys got this. Some of you guys got this. Okay. All right. So the correct answer is there's a weight acting down. You can either label it mg, what I usually do, right? Or say, or F sub g, like force due to gravity. Right? This same idea, right? So just pick one. Okay, you guys go. Okay. And you guys also drew a normal force. I was seeing, right? And the normal force, is it bigger, or smaller, or the same size as the weight? Yeah, it'd be bigger, right? It'd be bigger. I'll call it F sub n, normal force, right? So that force is greater than that force, right? The normal force is greater than the weight for at the bottom, right? Because and if you're not quite sure, then hey, man, well, what if you speed this up spinning, right? Imagine what would it feel like if you're sitting in that carriage and this turns into a centrifuge. It's like zoo, 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 zoo. At the very bottom, oh, yeah, I bet you would feel really heavy, right? And the scale pushing up against you would read a huge normal force, right? That's probably not the answer they look for. I think they wanted you to justify or explain why, right? I think their explanation would probably do something with the fact that you're on a curved path. Guys, if you're moving on a curved path, does there have to be a net force on you? Yes. And that's called what kind of force starts with the C? Centripetal, right? Now, guys, are you ever going to label a force vector centripetal force? Are you ever going to do that? No, right? Because centripetal force is just some net effect that's keeping you on a curved path, but it's always provided by one of your classic forces. In this case, a difference between, if you take normal force minus the weight, there is a difference. There is a net force, right? And guys, the centripetal force always points which way? Towards the center of the circle, which in this case is directly up. That's probably the justification they're looking for of why normal force would be greater than the weight, okay? So the net force is upward towards the center of the circle, right? You guys see that, right? And if that's true, hey, I think maybe the next logical one to do would be, how about at the very top? At the very top, right? Okay. Can you guys draw a free body diagram at the top? Go ahead and do that. Free body diagram. You walk around the room and see who's getting this right. All right, winner, winner. All right, winner, winner. Okay, yeah. You guys are getting this. That is exactly right. All right. Okay. Check everybody else too that sorry didn't. Right. Right. So you guys saying it's the exact same weight as before. The gravitational force from the Earth doesn't change, right? But that normal force from the bathroom scale that you're sitting on, that does. And I saw, yeah, everybody was talking about it. You guys were all saying in this case, smaller magnitude than the weight. So I'm going to draw it that way, right? Right. So that the net force is now downward, but it's still toward the center of the circle. Guess that too, right? Oh, because what if this Ferris wheel goes haywire and actually does turn to centrifuge, like right? What happens to this normal force? Gets smaller, smaller, smaller. Could this normal force go to zero? Right. If it's like a crazy ride. Yeah, it could get to zero, right? That would make you feel weightless, wouldn't it? Right. In that point, when you just like fly off your seat, fly off. Right. Actually, which direction would you fly off? Would you fly off straight up, or would you fly off horizontal? Yeah, you'd fly off probably horizontal, or yeah, possibly if you were like, I guess the fact that you're changing direction. If this was going fast enough, if it's going like crazy fast, yeah, maybe you could like launch off over here or something, right? But if it was moving like just fast enough, right, like just the right speed, yeah, if this was an AP question, I would probably tend to pick the one that said like horizontal. It's probably what they want to boil it down to, something like that, right? Because that'd be the direction of your motion, your instantaneous velocity. Right? Yeah. Okay. So you guys good with that? No, realistically, Ferris wheel, you want to make sure you don't get sued by whoever's riding it. Okay. Yeah. You want the normal force to be existent, right? So you're not flying off. All right. How about these sides? How about right here? Let's have this rotating clockwise. You guys see how this is going clockwise? You guys see that? Clockwise? Right. So how about right here where you're kind of coming upish? Now, remember I said a constant angular velocity. That's going to be an important detail to get this free body diagram exactly correct. Okay. So, yeah.
Okay, I have a question a little bit. Like, if the normal force is what keeps the person on the Ferris wheel, then how come it's pointed away the Ferris
wheel? Okay, because say if you're like sitting on a scale, the scale is holding you up, right? Like if you're sitting on a chair right now, the chair is pushing you up, right? You're pushing down the chair, the chair is pushing you up, right? So, like the net force is still towards the center of the circle. Like if you take the difference between these two, there's still the weight down is more than the normal force up. So the net force is still towards the center of the circle.
Yeah.
Right. So the centrifugal force is still towards the center. Right. Yeah. But the scale is like trying to pull you up. So, right. Yeah, like that. Right. Okay. All right. Right. So let's see for this one right here. Did you guys draw a weight and a normal force? Right. Did you draw one of those vectors as larger than the other, or are they the same magnitude? How many guys think here? Draw us here. So I've got these set up. I'm not going to put the arrowheads quite on them yet because I want to ask you guys which one of these should be longer. Right. Right. How many of you guys think they should be the same magnitude? Same. Right. Yeah. I'm going to do that. Right. So again, it's the same way as before. Your weight doesn't change anywhere around here. Right? The force from the Earth. Right. Right. Yeah. In this case, the normal force from the scale would be exactly balancing out the weight. You'd have zero net force, as if you were just sitting in class right now at rest, as if you were moving up or down at constant velocity in an elevator. You wouldn't be able to distinguish the difference, right? And isn't that true in an elevator, right? You can't see the outside world. If you're at rest in an elevator or moving up at constant velocity, or moving down at constant velocity, every single one of those scenarios is this, isn't it? Right? Constant angular velocity for this wheel means, right, so constant speed everywhere. Yeah, these two forces are balanced, right? Okay, then for the last free body diagram, would that also be true right here? That'd be true right here, wouldn't it? Okay. Ooh, actually, this paper I have right in front of me, I might take this home and turn this into a poster. This would be a pretty good poster, wouldn't it? Yeah. Got mg, got normal force, okay, just like that. That completes that one, right? Okay. Now, how could that be different from what if you get a ball on a string? Here's a ball, string, right? And we're gonna free body diagrams for this work. Right? Right. Oh, let's say you fly this around with sufficient speed to make it around the top, because there's a slightly different version of this question where they turn this into a light bar. Right? You guys have seen something like that, right? Now, if it's a light bar, the bar could go compressive. The speed could approach 0 possibly as it's going around the top. You could have that, right? But if it's a string, notice I call this a string, right? Can it go around the top with 0 speed? No, right? It could with the bar, but not with the string, right? With the string, do you guys remember what is the minimum speed to get around the top for a string? Right, it's like the square root of GR, and you get that from. Well, actually, maybe I'll cover that here in a minute. Right, how you get the minimum speed is square root GR. Right, hold on to that idea because we'll come back to that. Right, right, let's do. Let's start at the bottom. We did before too. Right, so at the very bottom, what's the free body diagram? But this ball has a weight, right? It says the ball has a weight, mg, something like that. Okay. And okay, I see it's on a curved path. What other force is on this ball? The tension, and tension is pointing which way? Yeah, straight up, right? Oh, and you guys did draw the tension is greater than the weight, right? Hey, just like that. Actually, this one look nearly identical. The only difference is it's not a normal force, it's a tension. That's the only difference, right? Is that right? Is that true? Yeah.
Would there not be a centrifugal force on both sides as well?
Oh, yeah, you're right. Actually, that's a good point. Let me go back to here. Right. You're right about that. I guess if it's on a curved path, yeah, there would be maybe a little bit of a friction force. I'll call it F sub FR and F sub FR. F sub FR, right? Because yeah, you're right. If you did not have a tiny friction force that was lateral, suppose you had like a marble on the floor of this carriage, yeah, it would be like rolling around, like rolling towards the outside. Yeah, that'd be true. Yeah, that's a good point too. All right, good detail. All right, so back to the ball and the string. You guys good so far? Ball and string? Great. Right, now let's look at the very top. Let me add a detail to my premise here. Ball and string, vertical circle, constant mechanical energy. Let's say, and sometimes they use this term, sufficient speed to make it around the top. Right. So it doesn't just barely get around. It does get around and it makes around with, in fact, sufficient speed. Right. What's the free body diagram? Very top. Right. Walk around the room, see who's getting this. See who's going to get ball and string at the very top. Sufficient speed make it around the top. Look at this. We have sea lunch. Yes, we got another half hour here. Somebody's got it. Yeah, I haven't seen it. I don't know. I may have missed somebody. I don't know.
Is it like this?
Yeah. All right. And then you should put little areas. All right. Yeah. And then you got it. All right. So it's one winner. That was true. That would be good. No, this is also. Almost. All right, yeah, winner. All right, so got a few winners. Okay. So of course, you guys have the weight acting down, and it's the same weight as before. So I'll draw that. All right, so mg is your weight. Okay. All right. Now, if it just barely makes it around, then actually that could be the entire thing, right? And I'm gonna pick up from that to explain what's the minimum speed to get around. So we're gonna come back to that detail, right? But if you see where it says sufficient speed, oh, that didn't show up so well in my projection. Sorry about that. Like green, probably try to avoid that color, right? Sufficient speed to get around. Do you guys think that there's some tension in that string? Hey guys, which way does the tension pull on the ball?
Down.
Down. Yeah. Undo F sub T. The tension's pulling down, right? Tension's pulling down, right? right? Is there any upward acting force on that ball? No, there's no upward acting force. The tension is pulling down, right? You know what that also kind of reminds me of? This is a little bit different scenario, but it's a really similar looking free body diagram. What about a roller coaster going around a vertical loop? And you just change that to a normal force. The normal force from the track pushes down on the roller coaster part, right? Right. Now, if you think from the track's point of view, they can say Newton's third law of motion, the cart is pushing up on the track. Maybe that's an upward force, right? But from the cart itself, in this case, the ball, yeah, only forces are downward, right? Now, do you know whether to make one of these larger than the other? Like I drew tension is less than the weight. Is that universally true? Not necessarily, right? Like if you swing it on really fast, like yeah, the tension could be more than the weight. That's fine. Okay. All right. How about that? With that side quest to figure out what is the minimum speed. I said it was going to be square root gr. Isn't that what I said? Right. So, all right, spell out that premise. Right. What is the minimum speed for ball on string to go around top of vertical loop? Right, minimum speed. Okay, so you guys get what we're trying to solve for? Right, right. Or here's a different story with the same answer. If I put some water in a cup and I put the cup on a string and fly that around in a vertical circle, I did that a few months ago, right? Right. What's the minimum speed? Right, same idea. Right. So I'm gonna say right, the net force to keep it on the curved path, like I said, was the centripetal force, right? Right. So centripetal force, right, is, hey guys, what's the expression for centripetal force? mv squared over r, right? You guys also have m omega squared times r. I'm going to put that in parentheses here, equals m omega squared times r, right? Maybe that's from an angular velocity point of view. So you might get that question, but more likely you're going to get that version. Okay. Then, let me point out too, because you kind of have this as an AP formula, but kind of not. It's where is it? It's this one right here, kind of near the top. It says centripetal acceleration is v squared over r. Right, guess that. Right. Multiply by m, you get a force, centripetal force. So get that. Right. And isn't centripetal force just whatever force or combination of forces are allowing it to keep on a curved path? Right. So I'll say that's in this case the combination of weight and the tension force, both acting in the same direction. So I'll add them together. Right. Is that the case? Right. Now, this word right here, the minimum speed. Right. Well, if it just barely gets around, what does the string tension approach? How about 0, right? It's supposed to have water in a cup, and I fly that around in a vertical circle. You go a little slower, a little slower, a little slower. Right. At some point, that water in the cup, it's going to be in free fall just for one moment. Like if you're a fish swimming around the cup, you feel like an astronaut just for one moment, right? And the tension in the string would be 0. So I'm going to take this tension and go to 0 newtons. Okay. So the centripetal force is provided only by the weight. Right? You guys get that so far? Okay. All right. So combining these two ideas, I can say mv squared over r is provided only by the weight. Okay. What cancels out on both sides? Yeah, mass. So no matter what the mass of this ball is, it has the same answer to the question, what's the minimum speed? Because mass just canceled out. Right? Then, okay, now you would have to assume the mass of the ball is huge compared to the mass of the string. Sometimes string of negligible mass, I'll throw in that. So we're solving for v. And since I let the tension go to 0, I know this is also the minimum speed. So v minimum is, okay, well, 2 steps away. I'm going to cross multiply the r, g times r, and take the square root. Hey, that's exactly what I said it was going to be. Or I said it was going to be square root gr. There you go. Right? That right there would be a completely fair free response question. Right? So you guys ready to field that in case you get that? You guys go back? All right. So, all right, back to here then. We got this mostly finished. Let's just do a couple more free body diagrams. Right, so how about this one right here? Let's say the ball is going around also clockwise, just to keep it consistent with the Ferris wheel type, right? So That's tangential speed, tangential velocity, right? So right here, what forces are acting on the ball? Does it have a weight acting straight down? Yep. That's the same magnitude as before. So that weight, that weight, that weight, they're all the same. Try to do all the same. Shorter. Okay, guess that. And also, what other force? Tension, right? And the tension has to be aligned with the string. So the string can only pull in the same direction as it's aligned, right? So I'll call it F sub t, right? So guys, what is the net force on this ball? Is the net force straight to the center? No, there's actually two kind of acceleration the ball is going through. There's yeah, right. The net force is actually a diagonal like this, isn't it? Right, it's a little tricky, right? So there's two kind of acceleration. There's tangential acceleration, the ball is speeding up on the way down. And there's also the centripetal acceleration caused by the tension in the string. Okay, so two kinds, right? Okay, how about over here? Last one. Okay. Is the weight of the ball straight down? Yep. mg straight down. Is the tension still pulling straight in? Yep. It's of course providing the centripetal force. So F sub t, maybe something like that. Okay, is that true? Okay. Oh, you know what? I do have a fifth ball here. All right, let's do this one real fast. Does this one have the same weight as before? mg? Okay. And does the tension pull exactly aligned with the string? Probably something like that. F sub t. Are you guessing? Right, just like that. Do you guys see too? Okay, now maybe this detail I didn't draw exactly correct, but what happens to the magnitude of the tension going all the way around? Where's the maximum tension in the string? Who thinks they know? Where's the maximum tension in the string? Yeah, the very bottom. Yeah, very bottom, right? And after that, it gets smaller, 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 then smaller, and it's wouldn't be the smallest at the top, right? And possibly zero at the top, maybe, right? If it just barely gets around. Okay. You guys get that? All right, there you go. There's a Ferris wheel and a ball and a string.